Morning. Can everyone hear me? All right, great. So my name is Sara Willman, and welcome to Risk Management Professionals webinar series. Our producers, Max and Karine, will be in the background keeping us operational and taking questions. We're using a GoToWebinar interface to support our presentation, so if you experience any technical difficulties, please contact our office at 877-532-0806. We have staff available to help with troubleshooting. The image sizes for the presenter screen and PowerPoint presentation are adjustable, and we have a dialog box for questions. So if you have any questions during the presentation, please submit them in the question box, and after the presentation, we will include them in our question and answer session. This webinar series is part of RMP's ongoing outreach program. RMP's core competencies and expertise reside in EPA, RMP, OSHA, PSM, CALARP, and SCMS program development, HAZOP, LOPA studies and other hazard identification techniques, and a variety of other process safety and regulatory standards. There we go. So today, Jasmin and I will be discussing inherently safer design and how it can be applied to hazard and operability studies. Before I get started, here's another quick list of an overview of our company and the types of services that we can provide. Like I said, HAZOP, CALARP, PSM, RMP. So today I'll be presenting on the concepts of inherently safer design and some examples of methods to implement these concepts. There are four main components: intensification, substitution, moderation, and simplification. After giving you a good overview of ISD methodology, I'll turn it over to Jasmin so she can talk about how to incorporate ISD concepts into process hazard analyses, particularly for HAZOP studies. The main idea of ISD is to avoid hazards entirely, rather than installing and implementing systems to control them. Additionally, we want to minimize the severity of consequences even if something does go wrong. So we'll start off with intensification. Intensification is also referred to as minimization, and it involves decreasing or eliminating the inventory of hazardous substances. This can be accomplished in a variety of ways that can lead to specific benefits for a plant. Benefits of minimizing a chemical process include a reduction in the total number of process operations, which can lead to fewer startups and shutdowns. Fewer process operation leaves less room for error and less cycling of equipment through startups and such shutdowns. Another important benefit is that smaller inventories will lead to much smaller accidents. For example, storing smaller quantities of flammable materials in smaller vessels can often contain overpressure scenarios, and if an accident were to occur, the consequences would be less severe than a very large, high-pressure vessel explosion. Despite the smaller vessel being operated at higher pressure, the small inventory would not pose as much of a risk as the larger inventory. As with every concept I'm going to cover in this presentation, there are going to be a few downsides. For example, intensification can often require higher pressures and temperatures to account for decreases in volume. In turn, the complexity of a process can increase as well. Process complexity leaves room for more frequent equipment failure or operator error. In addition, a smaller plant means that employees will inevitably be in closer proximity to process equipment and therefore hazardous substances. One common way that intensification can be implemented at a plant is through storage capacities. A plant can reduce large amounts of storage by using hazardous substances immediately after they're produced or delivered. And this is, of course, not always a viable option for every plant, but is certainly something that can be considered by improving logistics or supply chain methods. Simply reducing the amount of storage or the amount of time that large quantities are stored can help reduce risk. Another specific example of intensification is the prioritization of low inventory for distillation. Distillation is commonly used in a variety of chemical processes, particularly in petroleum refining. The columns usually contain highly toxic or flammable liquids and vapors at very high pressures and temperatures, and therefore pose a significant safety risk. Distillation is an essential separation technique and, of course, can be very hard to avoid in certain processes, so it's important to consider inherently safer design ideas when designing and modifying distillation systems. The key is to lower the inventory and reduce the residence times of hazardous chemicals. This can be done by narrowing the base of the column so that it can't hold significant volumes of hazardous liquid for long periods of time, or by combining multiple cascading columns into one. If possible during the design process, the plant designers could even consider other separation methods besides distillation for their process if possible. So moving on to the next principle is substitution. Substitution, by definition, involves substituting safer materials for hazardous ones. For example, avoiding highly reactive or flammable agents, trying to design the process using materials that require lower temperatures and pressures. One common area where substitution can produce safety benefits is in heat transfer fluids. Heat transfer fluids are often flammable hydrocarbons or toxic refrigerants such as anhydrous ammonia. If possible, the use of less hazardous substances would be inherently safer. Flammable heat transfer fluids could be rendered not flammable by using certain types of hydrocarbon blends, and refrigerants other than ammonia could be utilized to help make a process less toxic. Unfortunately, downsides to substitution include economic factors and reduced process efficiency. Hazardous materials are, of course, often used for distinct reasons, and it may not be possible to substitute them without incurring significant operating or chemical purchasing costs or reducing the efficiency of the process. For example, anhydrous ammonia is widely used in refrigeration for its excellent heat transfer efficiency and low environmental risks. So it's often difficult to avoid the use of anhydrous ammonia in large-scale refrigeration. So in this case, the idea is to keep ISD principles in mind. So if substitution is not possible, another ISD method may be suitable, such as reducing the inventory of the ammonia through intensification. So some examples of substitution. It's an ISD principle that is, of course, very applicable on a case-by-case basis. So I'll provide a handful of specific examples of substitution in the industry. For example, many plants use simple soap and water for cleaning, as opposed to using toxic or flammable solvents. Ductile materials should be emphasized over brittle ones, because brittle breakage is often much more dangerous and sudden than ductile materials. Toxic solvents can be used in material coating processes. So to be inherently safer, maybe using dry powders with UV rays and electron beam radiation might be a more safe way to manufacture the coatings. A particularly specific example is the use of ISD in ethylene oxide manufacture. It used to commonly involve catalyst tubes that are cooled by boiling kerosene under pressure. But in 1974, the disaster at a chemical plant in Flixborough, England, killed 28 people, which I'm sure many of you have heard of this disaster. The plant manufactured nylon 6, and the hasty addition of a bypass line likely led to this incident. And so after the incident, vapor cloud explosions were much better understood. So it influenced other industries using boiling hydrocarbons as heat transfer fluids, like ethylene oxide manufacture, to use water instead. So the next principle is moderation, also known as attenuation, which involves using hazardous materials, but storing and processing them under the least hazardous conditions. An example of this is storing chemicals as refrigerated liquids at atmospheric pressure instead of under pressure at ambient temperatures. This reduces the risk of overpressure scenarios and potential chemical releases or explosions. Another example is to store toxic substances in dilute solutions, like aqueous ammonia, which is used in many applications over anhydrous ammonia due to its inherent safety. So one example of moderation exists in the production of phenol. Phenol production involves a reaction stage that operates within 10 degrees Celsius of the temperature where a runaway reaction can occur. So to help with this, a water dump tank is installed as a safety system. A way to avoid this problem and even render the dump tank completely unnecessary would be to increase the reaction volume, which would decrease the necessary temperature. And so a takeaway from this example is the idea that inherently safer design is meant to reduce the necessity of complex safety systems by making the process conditions themselves inherently safer. Now, of course, higher volumes also pose another kind of risk. So naturally, ISD will often lead to both benefits and downsides. So the goal of the designer is to determine what trade-offs are acceptable and what designs ensure that the benefits outweigh the downsides. Keeping in mind that reduction of the severity of consequences is one of the main goals of designing an inherently safer plant. Other examples include the storage and transport of hazardous materials. They should be stored as dilute solutions or in another form if possible. For example, chlorine can be stored as sodium hypochlorite. While sodium hypochlorite isn't not exactly non-toxic, it's certainly less dangerous than pure chlorine. So the final principle of ISD is simplification. Simplification is the act of reducing process complexity. The benefits of this method are that the plant contains less equipment, simpler systems provide fewer opportunities for human error, they are typically cheaper than complex processes because they don't need as much equipment, valving, or piping, and the plant would be able to use less complex protective equipment on top of it. Simplification can be achieved in a variety of ways. Stronger or more resistant equipment that can withstand high pressures can be used in lieu of complex relief systems that's on top of the already existing equipment. Similarly, materials that can withstand high or low temperatures reduce the need for complex control instrumentation. In general, the simplest plants involve few moving parts. Equipment should remain stationary as much as possible. So one of the most important simplification techniques that can be easily overlooked is the relocation of equipment. So sometimes you'll find that, let's say, two tanks that interact with each other are located on completely opposite sides of a plant. That'll increase residence times and the need for complex valving along the way. Another example is if a tank that must be easily accessible by operators is located behind three other large tanks, requires an operator to turn a bunch of corners before getting to it. This can increase operating procedure complexity as well as increase the time for an emergency response if needed. So the goal would be to, of course, arrange plant equipment in such a way that everything is easily accessible and that process flows can easily and simply reach their destinations. Besides the main four ISD concepts, there exist many other methods to consider when designing and modifying an inherently safer plant. For example, limit the effects of dangerous potential consequences by changing designs or reaction conditions rather than adding protective equipment that can fail or be neglected. Avoid situations that can lead to a domino effect of failure. Make incorrect equipment assembly virtually impossible. And make sure that the status of installation and the status of the equipment is also very clear. Like, it should be very obvious if a piece of equipment is not installed correctly or is functioning improperly so that it can be taken care of right away. Related to that, ensure that equipment is designed to tolerate poor installation or poor operation without a major failure should the installation be not up to par. So control of the process should also be simple and easy. It is recommended to emphasize control via physical principles like pressure and temperature gradients rather than with a bunch of control equipment and extra unnecessary control equipment. Ensuring that any computer software also used to control the system is reliable and designed by someone knowledgeable of the process. Have standard operating procedures, clear instructions. Make sure to consider the entire life cycle of a process. Problems and hazards that can arise during construction and demolition can be overlooked. So it's important to focus design not only on normal operations of the plant, but also from the ground up and back down. So lastly, the passive mitigation. Passive mitigation doesn't run high risk of mechanical failure or lack of activation. In fact, the whole idea of passive mitigation is that it doesn't need to be activated. So in general, passive mitigation systems should be emphasized over active mitigation systems. So a common misconception about ISD is that these concepts are expected to be utilized in any way possible. A plant should be 100% inherently safe, but the reality is that it's impossible to do that. No chemical process can be 100% safe, but the goal that we should all have as engineers and operators is to ensure that we are always thinking critically about designs and modifications to processes, keeping safety a top priority. The idea behind ISD is not only to prevent accidents from occurring, but really to mitigate the severity of consequences should an accident happen. Like my example from earlier, one might intensify their plant by reducing the volume of all major tanks, therefore reducing hazardous chemical inventory. This means their plant will likely run at higher pressures, but in the event that something does go wrong, the release would be much more insignificant due to the low inventory. As with all these concepts, there are always going to be trade-offs. Deciding what is most beneficial to the plant and what downsides are acceptable is also influenced by economics and process efficiency. Essentially, not every concept here is going to work for every situation, but ISD should be part of an engineer's mindset, hence the idea of it being a philosophy. And these concepts should always be taken into consideration when designing potentially dangerous process plants. So thank you. I am now going to hand it off to Jasmin, who's going to talk about how these ISD principles can be incorporated into HAZOPS studies.
All right, thank you, Sarah. Am I coming through clearly? All right, perfect. So thanks, Sarah, for reviewing the principles of ISD. I will now review how to incorporate these ISD principles in HAZOP studies to improve the overall safety of your plant. So traditionally, the goal of a HAZOP is to identify hazards and mitigate or manage these hazards through safeguards, which are typically add-on safety devices and procedures. However, as Sarah mentioned, ISD aims to eliminate or reduce hazards instead of managing and controlling these hazards. In order to make the most out of a HAZOP study, one method is to use ISD checklists and principles to identify opportunities to eliminate or reduce hazards within the HAZOP study. Alternatively, another method is to use the HAZOP as a tool to identify hazards and then generate ideas for ISD using your existing HAZOP. When using the risk ranking matrix in the HAZOP, the severity must be evaluated based on the consequence, and the likelihood is typically reduced by adding layers of protection or safeguards. So instead of considering safeguards to reduce the likelihood, the design team should first consider ISD alternatives to reduce the severity of consequences. So this is where you can really brainstorm ideas for inherently safer design in your plan. I will review each of these methods, beginning with ISD checklists. So ISD checklists can be added at the end of HAZOP studies to stimulate thinking of inherent safety review for the overall plan, or they can be added within each node of a HAZOP study to stimulate thinking of inherent safety review for specific subsystems. Checklists are intended to promote out-of-the-box thinking for your team and to generate ideas that might be usable in an existing facility or a plant of the future. These ISD checklists should not be used in the rote yes and no manner like you're used to seeing for human factors and facility siting checklists in your PHAs, but the idea is to consider what might be possible and then determine what is feasible for your system. Checklists should be reviewed periodically throughout the life cycle of your process, so you may consider including ISD checklists within the 5-year PHA requirement if you are CALARP RMP PSM regulated. These should be reviewed periodically since as technology changes, what was once impossible becomes possible, and what was once infeasible becomes feasible. So to begin, here are examples of intensification or minimization checklist questions that can be added to the HAZOP study. These questions can be rephrased by the facilitator to prompt maximum creativity of your team, such as using the wording, how might it be possible to do the following, instead of, is this possible to do the following? Intensification or minimization checklist questions include, is the storage of all hazardous gases, liquids, and solids minimized? Can equipment sets be combined to reduce overall system volume? Can pipeline inventories be reduced by feeding hazardous materials as a gas instead of a liquid? Are just-in-time deliveries used when dealing with hazardous materials at your plant? Are all hazardous materials removed or properly disposed of when they are no longer needed or not needed in the next however many days at your plant? Are attempts made to completely eliminate raw materials, process intermediates, or byproducts wherever possible in your system? And can process conditions be changed to reduce production of hazardous waste or byproducts? So as you can see, these questions, for the most part, center around minimizing in-process inventories of hazardous raw materials, intermediates, and our finished products. So here are examples of substitution and moderation checklist questions. For substitution, checklist questions include, is it possible to substitute less hazardous raw materials in your process? For example, can a non-combustible material be used instead of a flammable? Can a less volatile material be used? A less reactive material be used? A more stable product be used? Or less toxic materials be used? These are all branch-off questions that originate from your initial substitution checklist questions. For example, in refineries, this can be achieved by using sulfuric acid for the alkylation unit rather than hydrofluoric acid. Or if you have a selective catalytic reduction system, aqueous ammonia can be substituted for anhydrous ammonia. Another question is it possible to eliminate hazardous raw materials, process intermediates, or byproducts by using an alternative process or chemistry? Then is it possible to use utilities with lower hazards? For example, can low-pressure steam be used instead of a combustible heat transfer fluid? Also, is it possible to substitute less hazardous final product solvents? So as Sarah mentioned earlier, can a water-based product be used in place of a solvent or oil-based product? As you can see, substitution checklist questions center around finding an alternative chemicals or processes to completely eliminate the hazard. And moving on to moderation checklist questions. Checklist questions include, can potential releases be reduced via lower temperatures or pressure or elimination of equipment? Basically, this question poses whether a process can be operated at less severe conditions using any other route. For example, can design upgrades improve the thermodynamic or kinetic efficiencies of reactors, like improved mixing or heat transfer, to reduce the operating temperatures or pressures at your plant? Or can you change the order in which raw materials are added to reduce the temperatures or pressures? Then another question is it possible to make a reaction conditions less severe, like less severe temperatures and pressures, by reusing a catalyst or by using a better catalyst? Is it possible to dilute hazardous raw materials to reduce the hazard potential in your plant? For example, can aqueous ammonia be used instead of anhydrous? Can aqueous hydrochloric acid be used instead of anhydrous? Can sulfuric acid be used instead of oleum? And can dilute nitric acid be used instead of concentrated fuming nitric acid? These are all questions you can pose to the team depending on the chemicals in your process. Another question is, are all hazardous gases, liquids, and solids stored as far away as possible to eliminate disruption to people, property, and the environment in the event of an incident? Basically, you want to make sure the storage of your chemicals is far away to avoid knock-on or domino effects in the event of an incident. As you can see, overall, moderation checklist questions aim to lessen the hazard potential by changing operating conditions, their chemicals, or locations of these chemicals. And then finally, here are examples of simplification checklist questions to be added to the HAZOPS study. One question is, are equipment and procedures designed such that they cannot be operated incorrectly or carried out incorrectly? For example, can your displays be simplified? Is valving, piping, or hosing designed to prevent connection errors at your plant? Can vibration be reduced with better equipment? Is the use of open-ended valves minimized? Or can the number of connections and paths be reduced in your system? Another question is, are machine controls located to prevent unintentional activation while allowing easy access for stopping the machine? Are all manuals, guides, and instructional materials clear and easy to understand, especially those that are used in an emergency situation? For example, can procedures be simplified by reducing excessive reliance on human action to control the process? Can equipment be eliminated or arranged to simplify material handling? For example, can equipment be gravity-fed instead of using pumps? Can the congestion of equipment be reduced, or can flow paths be shortened? And then finally, can distributed control system modules be simplified or reconfigured such that the failure of one module does not disable a large number of critical control loops? So simplification checklist questions aim to simplify equipment, procedures, and controls. So this figure shows a template example of how the checklist questions I mentioned earlier can be incorporated into HAZOP study worksheets. First, the HAZOP facilitator asks the question of the checklist listed in the question column, and then the team brainstorms potential opportunities to implement ISD within the specific HAZOP node. Next, the feasibility of incorporating the ISD can be discussed and documented in the feasibility column. Here you ask, is it possible for your plant to implement this ISD? Is this feasible without introducing additional hazards? The ultimate potential consequence related to the checklist question is then recorded in the consequence column. And existing case safeguards are documented, which are risk ranked. The recommendations column is used to address the specific consequence by considering your inherent safety design you brainstormed earlier. So for example, in this figure, the HAZOP node being considered is a storage of a chemical in bullets near the unit. In the first row, the question is introduced. Can hazardous raw materials inventory be reduced? This is a minimization checklist question. Then the potential ISD opportunity is brainstorm, and the team arrives that they can lower storage tank volume or eliminate storage if possible, and that is documented in the potential opportunities column. Next, the feasibility of lowering storage tank volumes further or eliminating storage is examined, and in this example, the team discussed that it is feasible for one storage tank to be eliminated. Then the worst case scenario or consequence of having large amounts of hazardous raw materials inventory is discussed, and the consequence is that there could be a potential release from storage resulting in a vapor cloud explosion. The severity of this consequence is ranked in the severity column. Then current safeguards are listed, such as administrative controls to limit levels in tanks. And the likelihood of the consequence, considering these safeguards, is ranked, producing a risk ranking. The final item is a recommendation, which is based off of your ISD brainstorm you considered earlier. So this is when you evaluated potential opportunities and then determined their feasibility. For this example, the recommendation is to eliminate one of the 5 flammable storage bullets to reduce potential releases from storage, which uses the minimization ISD principle. So that concludes how checklist questions can be added to HAZOPS to encourage ISD consideration. Next, I will discuss an alternative method to incorporate ISD into HAZOPS by using an existing HAZOP or building off of your traditional HAZOP study to brainstorm ideas for ISD. So as I mentioned earlier, in conventional HAZOPs, hazards are mitigated or managed by safeguards, which are typically add-on safety devices and procedures. When using the risk ranking matrix in the HAZOP, the severity is evaluated based on the consequence, and the likelihood is typically reduced by adding layers of protection or safeguards. Instead of considering safeguards to reduce the likelihood, the design team should first consider ISD alternatives. As this figure depicts, the most effective control to reduce the severity of a consequence is elimination or substitution. Elimination is also referred to as minimization, which are ISD principles. So elimination or minimization is considered a first-order inherent safety measure, while substitution is considered a second-order inherent safety measure. Then this pyramid lists your more typical controls, which are used to reduce the likelihood of a consequence, including engineering controls, administrative controls, and PPE. Engineering controls are the third most effective control, which uses passive and active safety systems such as dikes or berms or pressure regulating devices. The next most effective control is administrative controls, which includes procedural protection layers. And finally, PPE is the least most effective control measure. So for this method, instead of leading with the ISD checklist question to brainstorm ideas for ISD consideration, this method uses a traditional HAZOPS study to identify hazards, and then the HAZOP facilitator sets the safety objectives such as minimization, substitution, moderation, or simplification. This figure shows a template example of how ISD strategies can be incorporated into existing HAZOP study worksheets using this method. The hazard evaluation team reviews the cause, consequence, and existing safeguards developed during the traditional HAZOP study. And then the team identifies possible opportunities for eliminating the hazard or reducing the risk through ISD strategies, which is documented in the opportunities column. The feasibility of this strategy is then documented in the feasibility column, and potential recommendations are documented in the recommendations column, considering your 4 ISD strategies: minimization, substitution, moderation, or simplification. Potential recommendations that may address the concern are listed in order of first-order inherent safety measure, which is minimization, second-order inherent safety measure, which is substitution, and then engineering or administrative controls recommendations are listed last. So for this example, or in this figure, the process node is feed to the reactor. The first row identifies the cause as high water content in the feed tank. And the consequence of this cause is documented as excess water in the reactor may lead to shorter run life due to catalyst fouling, and the worst case scenario is that excessive water may cause a runaway reaction. The safeguards for this consequence include operator monitoring of process conditions. So this is really where the team can brainstorm ISD alternatives to relying on operator monitoring of process conditions. In this case, the concept of minimization is used to avoid a hazard, and the opportunity arises to evaluate a way to eliminate water from entering the reactor rather than using controls. So rather than relying on your operator continuously monitoring. The team then examines whether it is feasible to eliminate water from this process and documents it may be feasible to switch to a clean tank without the potential for water introduction by making minor piping changes. Thus, the recommendation is to change the feed to the reactor from the tank that currently has high water settlement to a tank that has a clean feedstock. So I have now discussed both methods of incorporating ISD and HAZOP studies. However, that begs the question, at what level of detail in your study should ISD be considered? So for both methods of incorporating ISD, this can be performed at the node level when you're examining a particular subsystem, or at the overall process level when you're examining the entire plant. But when examining ISD at the overall process level, however, the opportunities for ISD are limited as the overall process is simplified, and stimulating ISD considerations for the team presents more of a challenge for the facilitator. If the study is conducted at the detailed node level, this may result in additional considerations being given to smaller but important details. For example, at the macro level or the overall process level, it may appear that the hazardous chemical in the process cannot be substituted. But on a micro level or node level, there may be opportunities to do so for specific areas or items of equipment. Therefore, it is recommended to apply the ISD approach to each node within the HAZOP study rather than examining the process as a whole. Another question that arises is, why should your facility incorporate ISD into HAZOPS other than to improve the overall safety of your plant? So hopefully improving the overall safety of your plant is reason enough. But if you're a CALARP Program 4 facility, which means if you are a refinery operating in California, this is a regulatory requirement. As part of the new CALARP Program 4 regulations, you are required to perform a hierarchy of hazard control analysis. A hierarchy of hazard control analysis, or HCA, is required to be performed for all PHA scenarios that identify the potential for a major incident, whenever you have an MSC, whenever an incident occurs at your facility, or during the design or review of new processes. This HCA can be performed in conjunction with the PHA schedule, and the HCA uses information provided by the PHA MOC or incident, namely the process safety hazards that are identified by these studies, to identify, analyze, and document all inherent safety measures and safeguards in an iterative manner to reduce each hazard to the greatest extent feasible. So for each process safety hazard, the team shall first develop written recommendations to eliminate the hazards using first-order inherent safety measures, and then the team shall develop written recommendations to reduce the remaining hazards using second-order inherent safety measures. And remember from that upside-down triangle figure we reviewed earlier, elimination or minimization is considered a first-order inherent safety measure, while substitution is considered a second-order inherent safety measure. These are both ISD principles. Therefore, the HCA requires facilities to consider these ISD principles to reduce hazards, and it is linked to a regulatory requirement if you are a refinery in California. This is just something to keep in mind. So that about concludes my portion of this presentation. I just wanted to let you know that I discussed how to incorporate ISD into HAZOPS studies using two different methods. However, Risk Management Professionals has a previous webinar which discusses evaluating ISD at various levels of process design, which is available on our website. This reviews the advantages and disadvantages of using ISD at different levels of process design, from the conceptual design phase, feed phase, detailed design phase, procurement or construction phase, to the plant operating life cycle. So if you're interested in this topic further, please feel free to visit our webinars page of our website. So here are the references used to create this presentation. And we have a variety of webinars and conferences coming up, including Safeguard Protection Analysis for CALARP Program 4 facilities, presented by Steve Marr and John Johnson on March 27th. We have a April webinar presentation presented by Mac Lopedal covering the importance of P&ID labeling. We'll also be present at the 2018 IIAR National Conference, which Sara Willman, who presented earlier, will be attending, so feel free to say hi to Sara if you're there. And RMP will also be present at the 14th Global Congress on Process Safety. So if you're attending either event, feel free to visit our booth. Oh, sure. Yeah. So it looks like we have a correction to this slide, actually. Okay, so I've just received news that we're actually presenting two papers at the 14th Global Congress on Process Safety.
And also the March 27th webinar is on doing HAZOPS and open studies.
Oh, and our March 27th webinar is actually performing HAZOP on LOPRA studies remotely. That's the topic that will be covered instead of safeguard protection analysis. So thank you, Steve, for bringing that up. That clears up a lot. All right, now we can open it up to questions. Sara and I are happy to answer any questions you have. And just as a side note, the audio and PowerPoint presentation are being recorded and will be available for viewing in about a week.
Okay, hello everyone. So, first question. Are there any cyclical requirements for HCAs?
Yes, that's a good question. So HCAs are required to be performed or updated every 5 years. And that's on top of the requirement if you have an incident at your facility, have an MOC, or perform your PHA, you're supposed to also perform HCAs as part of those instances, as well as doing them every 5 years. So the cyclical requirement is you're supposed to perform HCAs every 5 years.
Thank you. When is the best time to implement ISD principles in an operating plant?
Okay, so of course, the best time to implement these is usually in the design phase, before anything's been completely built or designed. You want to analyze these principles so that you can incorporate this more easily before things actually start up. But that doesn't mean that you can't incorporate these principles throughout the life cycle of the process. There's always modifications that can be made. There's always things that can be reevaluated and redesigned, even if a plant has been in operation for 20 plus years. However, it is important to note that it does become increasingly more difficult and more expensive sometimes to implement ISD concepts later in the process life cycle. And we actually do discuss a lot of that in the previous RMP webinar that we have on our website.
Thank you. Those are all the questions.
All right.
Thank you so
Thank
much.
you for your time.